even though it talks about the contact process in chapter 8, it really gives clarification here. In your textbook on page 198, it will talk about the conditions for sulfuric acid. So there you can fill in the specific conditions, and once again, make sure to avoid vague phrases like high temperature. So we want to be as specific as possible. What are the exact conditions that are required for the content? All right, this problem here, I know we started off in class kind of working through for the carbon monoxide problem. Remember here you're doing the ice bucket challenge, so we're doing how much changed and what did it end. So we're kind of starting off, and anytime you're going through any kind of reaction process, we know here it's a 1 mole, 1 mole, 1 mole, 1 mole. So when I'm changing, I'm having to subtract 1x, so I'm losing some 1 mole of content. Here I'm also losing a mole of some amount. Here I have to gain some mole, and here I have to gain some mole, because once again a 1 to 1 to 1 ratio. So as far as the number of moles, so that's how much I changed. What would I end with? What would my end concentration as far as just moles? So I would take my initial, so I'd have 0.7 minus x for the first piece. It'd also be the second, that'd be the same for this next piece, so 0.7 minus x. Then I'd also have this one would be the 0.3 plus x, and this one would be 0.3 plus x. That wouldn't affect, because that would be my concentration expression. So if this 1 was a different number, it would change my values. But I can write my case expression. We know it has to be the equilibrium concentration has to be of our products over our, so I got the concentration of CO, I have the concentration of H2O. We're dividing that by the concentration of CO squared and the concentration of H2. So we're doing, once again, products, concentration of products divided by concentration of reactants. And I can just now go ahead and plug these numbers in. All right, so when I plug the numbers in, we can see here's our Kc value. All right, our Kc value 1.44, and we get that just plugging in our concentration of CO into CO, concentration of H2O into the H2O. And now it becomes a algebra problem that we're going to have to end up using. So I'm going to multiply these two numbers, and end up trying to solve and see what is the actual value of x. What is my number of moles or my concentration for each individual specific item? All right, so after go ahead and multiplying these out and kind of foiling it out, we get 0.09 plus 0.6x plus x squared for our top, or that green function there. The blue, then when I multiply these out, we get 0.49 minus 1.4x plus x squared. We can see, all right, well, I have a value that we can go ahead and now cross multiply and start solving for x and go through that process. All right, so you should be able to do that. All right, a couple of things are going on in this problem here. We're looking at what actually takes place here. How do I know it's endothermic? Here I have a positive delta H. So positive delta H we know, so I know it's endothermic. So what happens in an endothermic reaction if you increase the temperature? So we know when it increases the temperature in an endothermic reaction, because technically you can kind of think about, even though it's not there, we can think about an endothermic reaction, heat being there. If I increase the temperature, it's going to push the direction towards the right, because we're adding more reactant, so to say, even though it's technically not part of a reactant, adding more reactant, pushing the direction in the formation of the products. So it has to go right. So we can instantly eliminate C and D, because those are both talking about an equilibrium shift towards the left. Well, that doesn't happen at an increase of temperature on an endothermic reaction. That would be an exothermic, but not endothermic. All right, now we just got to look at what happens to the volume. Does it increase only because of a shift of equilibrium, or does it increase because of a shift of equilibrium towards the right and also because of thermal expansion? Well, if you're increasing temperature of molecules, what do you know has to happen to the molecules? The molecules have to be moving a little bit faster. Therefore, they have to be bumping into each other a little bit faster. So we're going to have to get some thermal expansion and also a shift to the right of the equilibrium, causing a little slight volume increase. Please pause the video, try to figure it out yourself before attempting to move on. So pause first. This one, talking about Le Chatelier's principle, you can look that up in your textbook. It's really easy and simple to just kind of look up as far as stating. If it says state, all it's looking for is what is a simple definition of Le Chatelier's principle. And remember, we're thinking about Le Chatelier as like a seesaw. So anytime you have a seesaw at equilibrium, if I change the balance of this seesaw, so if I shift it any direction, so if the seesaw all of a sudden shifts that direction, well, it's going to automatically do something to stabilize and equal out. So we have to get this stable configuration in order to so that you can look up. All right, here we go. For temperature, and looking at this expression for temperature, and here, what do we know from our reaction? Well, here I see a negative delta H. What does that tell me? That tells me that this reaction is, we know that from last, that tells me that this has to be exothermic, right? Well, if exothermic, that means that heat has to be on my, so I have to have heat on this side of my reaction. I have to have heat as far as being over here as a product. So if I increase the temperature, it's going to cause a shift that way and not, so I'm trying to find a way to get more product. So I don't want to add anything on the product side. So as far as temperature, we need to decrease the heat in order to get more product. Why? Well, decreasing the heat takes away product, therefore shifting in the direction of product formation. So if I decrease the heat, once again, we're going to shift in the direction of product formation because we are taking away from the product, and therefore the reaction has to shift in the direction of product formation. All right, so that would be the explanation for temperature. Explanation for pressure. Well, in pressure, we're looking at how many molecules are there, how many actual pieces. So we have one CO molecule. I'll do that in black. And what do I know? I have 2 hydrogen molecules, so I have 2 over here. And that would be my products. So that's going to be my reactant side. And on the product side, I have 1 mole of methanol. All right. So for pressure, anytime if I increase the pressure any direction, it's always going to shift in the direction of the one that has the fewer molecules. So which side has fewer molecules? Well, right now we know our product side has fewer molecules. Over here there's 3. Over here there's only 1. So if I increase the pressure, so if pressure goes up, we know it has to shift in the direction of the products because it's going to shift in the direction of the side that has fewer molecules found on it. All right, so problem 4, it says I got 2 moles of hydrogen gas, 0.15 mole of iodine gas, so I have this nice looking problem. Here I kind of give you a hint already in the problem. Pause the problem, see if you can do it. It's similar to problem that we did in class to see if you did it right or not. But we know we have to do our Aice thing. That's kind of what I told you. Remember, that stands for initial. So we're going to write out, well, we have hydrogen, I have iodine, and I have HI. Right? So we know originally I have 0.2 moles of H2. I have 0.15 moles of I2, and originally I have 0 moles of HI. So it tells me though that I have an equilibrium mixture, so it says at equilibrium it has 0.26 moles of HI. So at equilibrium it has 0.26. All right, we can go ahead and put in all our change pieces. We know this has to change by some amount of 1 moles. this has to change by some amount of 1 moles, and this HI had to go up by 2 times X. Alright? So if that's 2 times X, I can kind of solve for X to see, well, because 2X has to equal the 0.2X. So if 2 times X equals 0.2X, that means this X had to be what? Had to be 0.13. So it had to decrease by 0.13 for each one. So this equilibrium here, to do the change, or the end, what would I end with? Well, it's 0.2 minus 0.13, or 0.07. This would be 0.15 minus 0.12, or 0.02. So when I write my equilibrium expression, we know it has to be products on the top, so it's HI, but it says there's 2 of them, so that's got to be squared. So it has to be some number squared on the top, so therefore A can't be right. It has to be some number of H2 times some number of I2, and we're just going to put our numbers in, see which one works. Well, the only one that works then would be C. So looking at the next problem here in our setup, where it says explain what is meant by the term dynamic equilibrium, it will just be a straightforward definition. Writing the expression for the equilibrium constant, that's just writing out your KC, so concentration of products over concentration of reactants. The last one here, however, says for this equilibrium we're given a value, so I know I have a KC value of 4, so I can write that out. I also have a mixture containing 0.5 of ethanoic acid, 0.5 of methanol, 0.1 mole of ethyl ethanoate, which would be this, so it's just telling me all of these compounds, and 0.1 of water. So I know I have 0.5 moles, so I can set up my Aice table, change, end. 0.5, I have 0.5. I'm just kind of working through these. That would be my 2 reactants. My 2 products are 0.1 and 0.1. Once again, a 1 to 1 to 1 to mole ratio. So this is going to be almost identical to problem 2. Well, here we're having a change. So the reactants have to decrease by some amount X. The products have to increase by some amount X. And so therefore the end concentration in this scenario would be 0.5 minus X, and then for both of these, and this would be 0.1 plus X for both of these. So I would go through and set up that whole expression, setting it up equal to KC, going through just like we did for problem 2. So I can set up my expression. So I put in my KC value, which it told me a KC value was 4. So I'm going to set those values up, put in my concentration of my 2 products, concentration of my 2 reactants, and go through the process of solving for X. Now I can cross multiply these 2. I want to do that at the bottom, and we set that equal to what we had on the top, right? And go through and solve it out. All right, so once I get to that point, now I can start moving things around and get my x squareds on one side, my numbers, and just move everything to one side and set it equal to 0. So I'm going to move everything to this side. I'm going to take 1 minus 0.0, and now I can plug into the Pythagorean Theorem, minus b plus or minus the square root of b squared minus 4ac all over 2a. And we just need to think about this, whether I'm going to have to do the plus version or the minus version when I plug these values in. So what do I get when I plug them in? I'm going to get 4.2 plus or minus the square root of whatever 4.2 squared is. And so that's what you would get once you did your expression. Well, I know that whatever number I get cannot be bigger than what I started with. I started with 0.5. So whatever my change in x is. So remember we started with, so I can't get any, here's our starting. We started with 0.5, 0.5. I cannot get a bigger number than what I started with. So whenever I'm evaluating this expression here, I got to make sure that it doesn't come out to a value bigger than 0.5. So, well, I can see that if I do the add, it's definitely going to give me a value bigger than 0.5. So I know the only one that's going to be valid is 4.2 minus 2.4 divided by 6, and that would give me my change of x, which tells me my change of x was 0.3. So what do I end up getting for my concentrations? So it has to change by 0.3. So we can scroll back up. Well, our N concentrations, then we can just plug in for our value. So 0.5 minus x, which we know is 0.3. So I'd end up with 0.2, 0.2. This has to go up by 0.3, so it'd be 0.4 and 0.4. Would give me my final concentrations in the number of moles, which is what the question's looking for. All right, so our next problem here, number 7, it's asking for equilibrium concentrations again. So we're wanting to write the equilibrium expression for concentration. That should just be products. So we're just taking our two products over our reactant and write that out. Here it's calculating the Kc. We just plug these values in at 230, take these concentration values. At 465, take these concentration values and plug them in for each one and see what you get. Try it and see if you can come out with the numbers that I get. All right, so this is what we should end up getting for our Kc values for at 230 and 465. Now the question is, .ei3, is the reaction endothermic or exothermic? All right, so the way to explain .ei3 is here you're seeing a Kc increase. As I increase the temperature, my Kc is increasing. That is meaning that I'm getting more product formation for my reaction. I'm getting, so the top value of my Kc expression is increasing over the bottom value, right? So the only way to explain that increase in product formation is it had to have been an endothermic reaction, because we get more product formation in an endothermic reaction with a temperature increase. And so there's our explanation for .ei3. All right, for question 8, it's asking about it's basically just an explanation of Le Chatelier's. And really we're looking a little bit more at what are some specific conditions. So we have a reaction here. It's all in gases. So condition 1, what would happen if I did something with gas and I want to make more product? So I want to somehow increase the product. So I want to push it in that direction. Well, we can think about it in terms of pressure, and I can think about it in terms of concentration. Or let's just say, let's do the easy ones, pressure and temperature. All right, that would probably be the two easy conditions to spell out. Well, is it going to get a higher yield with an increase in pressure or a higher yield with a decrease in pressure? Well, if I increase pressure, remember, it's always going to flow towards the side of fewer molecules with an increase in pressure. So if I'm going to increase pressure, that's going to give me a higher yield, going to flow more towards the side with the fewer molecules to be able to stabilize and get less molecules. So we're giving me more yield of our methanol. All right, for condition 2, what happens on temperature? Well, we know it's exothermic. Exothermic, that means energy is being given off by my reactants. So I'm getting energy basically, or heat energy kind of produced. So here, if I wanted to not increase temperature, but I need to decrease temperature in order to get any kind of an increased yield on this side. As I decrease temperature, we're reducing the amount of energy being absorbed and then pushing it more towards product